Hey guys, Nick here, and today we're going to take a look at the beast of Physics 1, torque. Now, torque is the study of if forces make objects rotate/spin. Up until now, we've only dealt with objects translating, so sliding left, right, up, or down. But now we're going to worry about if forces and pushes make objects spin. And if so, we'll be able to calculate how fast they'll make the object start to turn. Now, a fair warning, this is a very tough subject. I called it the beast of Physics 1 for a reason. It's something that combines the difficulty of free body diagrams and forces with just a couple more extra steps. However, fortunately, I'll tell you that once you learn the subject, it isn't nearly as intimidating. It tends to stick very well, whereas free body diagrams can be very, very difficult to get down pat. On the plus side, torque is really useful in a lot of biomedical fields and also in most disciplines of engineering. Torque is like an extra tool you have in your bag. We're going to do an example on the biomed side for the muscles on a skeleton, and then towards the end we'll probably do a challenge example about wires holding up gates. You can imagine how that would extend to things like bridges, signposts, buildings, and things like that. So it is a useful subject for all its difficulty. All right, let's get right into the defining equation of torque. And as usual, we're going to do this using a motivating example. So let's pretend we have a bolt here, and there's a wrench gripping around it. Okay? And let's say I'm trying to loosen this bolt, so I apply a force of 10 newtons, and just for numerical sake, I'm going to say I apply it on a very long wrench 3 meters away from this bolt right here. Okay, and we'll be spinning around this point, so I'm going to mark this X here for the point that we'll be spinning around. Okay, and the question is that you might be asked, how much torque is caused by this force? Okay, and to solve this question, which is again just a motivating example, we're going to introduce the equation for what the torque due to a force is. Okay, the equation is going to be, and actually I'm going to galaxy pen this because of its importance. Torque, which is denoted tau, is going to be the force times this letter r, and this r is distance from rotation center, which remember I have marked with a little x here, to where the force is applied. So in our case, it's this distance right here between the x and where the push is, which I told you was 3 meters. So in this example, I have a force of 10 newtons times an r of 3 meters for a total of torque is 30 newtons times meters. Okay, and again, this is a completely new unit, newtons times meters. You've never seen this before. A torque is a totally new kind of quantity. It's similar to a force, how a force is a push. A torque is created by a force. It's not a new object, but it's created by a force, and it is going to be something that you use to describe how fast it'll start to rotate. So in this case, it'll be how fast will the wrench start to spin and unlock this bolt. And just one more time, I do want to emphasize, forces create torques. Alternatively, you can say this is torques are due to already existing forces. Okay? I'm going to choose the second one actually. You don't need to do something new to an object to cause a torque on it. If you're pushing on the object with a force, the torque is already being caused by that force. It's just that up until now we haven't cared about it. whenever you've been doing free body diagrams, you didn't keep track of if these forces were trying to make the object spin or not. You just ignored it, and you just worked on the lateral motion. But now we're going to consider the fact that these forces have been creating torques the whole time. Okay, as a quick modification, I'm going to use this same bolt example here. Let's say I don't push quite straight on this, or actually let me save that for 1 second. Let's say I push at a different location. So instead of pushing at 3 meters, let's say I push at 2 meters with the same force. The torque due to this, remember, torque is force times the distance between the rotation point and the application of the force. So in this case, I still have a force of 10, but now I'm only multiplying by a distance of 2 meters. So the result is only 20 newtons meters, which is less than this one, even though I pushed with the same size force. And that seems really, really strange. If I pushed with the same hardness, shouldn't the torques be the same? And the answer is, in general, no. You actually know this already. If you pull further out on a wrench, it's much easier to break a bolt loose because the torque is actually bigger there. Again, that's different than saying that the forces are different size. We just saw that the same size force of 10 newtons, depending on how far away you place it, can create a differently sized torque. When we get to energy, this will be sort of explainable in terms of how far the force is going to be moving as the wrench rotates. It'll be moving further for the 3 compared to the 2 meter application, but we're not going to worry about that for now. For now, all you need to understand is that you can create different sized torques by placing a force in different places, okay? And as you get further out, the torque is going to get higher because you're making R bigger. Okay, another generalization that we're going to need, and we're still going to use the wrench example, is what if we don't pull perfectly perpendicular to the wrench? What if we pull, oops, I'm going to just draw this a little differently. Let's say our pull is here, and let's say we pull with 10 newtons here, and let's say that this distance is still 2 meters, but let's say instead of pulling straight up, I pull diagonally with 10 newtons. Okay? The generalization to the torque formula that we're going to need to make is instead of having just F times R, afterwards we're also going to need to multiply by sine theta. And I'll tell you exactly what theta is, because just because 30 degrees appears here, you know, it could be a trap. I could be referring to 60 degrees, so I'll explain which theta it is in a second. But again, this happens anytime the force is not at a right angle to, and I'm going to put in quotes, R. Secretly, this whole time, R is this arrow that points from the rotation center in a line out towards where the force is applied. So in this example, this is what R looks like. So something perpendicular to R would be straight up and down, but oops, ours isn't. So we need to include this extra factor. Okay, and theta, the definition of theta is it's the angle between this orange R arrow and the force arrow, okay, which I'll redraw in green just for visual clarity. So if we compare the directions of these vectors, R goes like this, F goes like this, so the angle between them is 30 degrees. So in this case, to compute the torque, we're going to do the size of the force, which is still 10, times the size of r, which is still 2, but this time we're going to multiply by sine of 30, because again, we're not pulling at a perfectly right angle to the orange arrow. If we were, we would be doing times sine of 90 degrees, which is automatically 1. Okay? And if you plug this in, you get 20 times sine of 30, and sine of 30 happens to equal 1/2. So instead, you only get 10 newtons of torque for this pull, even though your force is the same size. So just like we had up above, we already saw that the same size force, if you put it in different places, even if they're both still right angles, can already produce torques that are different. But even further than that, even if you put the force at the same place, depending on if you point it straight up, like in this example, or diagonally upwards, you'll still get different numbers for the same force, or different torque numbers, even if the force was the same the whole time, which is really non-intuitive, but it is a fact. Some notation here. Often this quantity right here, r sine theta, is called the lever arm. If you're an engineer, you may hear it called a moment arm. Okay, all equivalent terms. Now, before we move on, this is sort of like a little addendum. Some professors prefer to write this equation in a different way, so your professor might have written it like this. Okay, I'm just going to redraw our wrench example. Some professors prefer to teach it like this. And again, this, you don't need to get this 100%. It might help out for some problems, but this is mostly for those of you whose professors taught you differently. Same situation here. 10 newtons and a lever arm, and a r of 2. Some professors, instead of writing it like this, they instead prefer to group f sine theta together. So in this case, f sine theta, they'll often write it as f perpendicular. So your professor is giving you options here. They're saying either you can multiply r times f, so 2 times 10 times sine theta, which is, let's see, sine theta is sine of 30. Or they're saying equivalently, since f sine theta and f perpendicular, which turns out to be this length, are the same thing, you can instead multiply the size of r times not all of f, not 10, but this length right here, which will be, if you do trigonometry on this 30, 10 sine of 30. I'm just going to write this in a different color. Okay, so either way, you're getting the same answer. However, some professors prefer to have you look at the problem and say, oh, only multiply by the component of the force arrow that's perpendicular to the orange radius arrow. And other professors will say, no, don't worry about breaking the force into components. Multiply the total size of the force times the total size of the r, and then multiply by the sine of the angle between them after. Now, still other professors may show you this equation. And again, if your professor doesn't do it this way, don't worry about it, you can move on. If your professor writes it like this, he's choosing to group r and sine theta together instead of f and sine theta. So what he means is, here's your force. Oops, let me keep my consistent color scheme. Here's your force. Here's your radius. Use only the part of the radius that's perpendicular to this arrow. So he's telling you, break your orange arrow into a right triangle. and only use this leg right here, so the part that's perpendicular to this green force arrow right here. Okay, and once again, we'll see that it's the same number. He's just chosen to package the sign with the R. So let's see, if this is 30, then this is 30, then this is 60, and again, R is 2. So the length of this leg is 2 times, I'm going to use this angle and use sine, 2 times sine 30. And again, your professor's instructions are, no, there's no multiplication by sine 30. You should just multiply by the length of this leg for your R, multiply by the size of the force, which is 10, and there's no extra multiplication by sine of 30 afterwards. The sine of 30 has been packaged into the fact that you're using this leg instead of the total size of R. And again, here, R and sine theta together comprise the lever arm, just like before. Again, if your professor didn't teach you this way, you don't really need to worry about this. Just understand that R sine theta, as I defined it above, as a group, is often referred to as the lever arm. And again, this is the general formula that you need to use, so I should probably put it in Galaxy Pen here. Whenever F and R are not perpendicular to one another. When they are, it simplifies to F times R, but if they aren't, you need to multiply by this extra factor of sine theta. Okay, perfect. Now we're going to go on to the concept of equilibrium. Now, just like how forces to the left could be balanced with forces to the right, clockwise torques can be balanced against, I'm going to use CCW for counterclockwise, against counterclockwise torques. And when they are, the object doesn't rotate. Okay, again, this is very similar to how if you had a 10 newtons push to the right on an object and a 10 newtons push to the left, they canceled out against each other. They fought against each other, and the net effect was the object didn't accelerate at all. Same thing here is if you have, let's say, a long stick. Maybe it's balanced on a pedestal, and you make a push down here, and you make an opposing push down here. Well, this push tries to make the stick turn clockwise, while this push tries to make the stick turn counterclockwise. If the torques due to this one and this one are the same size, then the total attempts to make the object rotate cancel out, and the object doesn't rotate. So in this case, you would have something like the counterclockwise torques equal the clockwise torques. Again, this is very similar to saying forces pointing to the right must be equal to forces pointing to the left in size. That way they cancel out. So we're quickly going to do an example on this. However, before we hit the example, I just want to make a key point here. And again, this is so we'll be able to do the example. A common question will be, so it makes sense if you tell me where a force pushes, where it goes. But what about the weight force? Where does the weight force, quote unquote, push or pull on an object? It isn't really at a point. And it turns out the answer is at the center of mass, which is usually the geometrical center of the object. But oftentimes in problems, you'll be told that, oh, this object actually isn't uniform. Its center of mass is slightly off to the right of the center, and they'll give you its x-coordinate. So that is, it turns out, where you should draw the weight force for a long object. Okay, now we're going to get into one of these torque balance equilibrium examples. And you'll see why we need this. Okay. Okay, so in this example, we have a 1 meter long meter stick. Well, I hope it's a meter long. And it has a given weight of 5.52 newtons. And it says it's rotating around this point right here. It's sort of held up and it's held up so it can only spin about that location. Now, in addition, we hang a mass from it of given mass 0.16 kilograms or 0.106 kilograms, and it tells us where it is located. It tells us that this distance is 0.683 meters. And the question is, what force do we need to apply here in order to keep the rod straight? Now, again, the general idea is going to be that the counterclockwise torques had better equal the clockwise torques in size. So let's figure out what the torques due to all the forces are on this rod and see what happens. Okay, let's first deal with the weight of the rod. Okay, so the weight of the rod, as we had just went over, where does that force arrow deserve to be drawn? And the answer is at the center of the stick, because, again, it says that it's a uniform stick. So over here at 0.5 meters away from the edge, there's going to be this downwards weight force from the weight of the meter stick. Oops, sorry, I should say W. Okay, and that one is a clockwise torque. Okay, next let's do this hanging mass. Let's see, we're given where its pole is located. It's at 0.683 meters, and it's of size little m times g, this force right here. And again, that's because the weight is a force. It's how hard gravity is pulling on this object. The size of the weight force is not the mass of the object. You have to multiply it by 9.8 to get the force in newtons. Okay, and then finally, let me put that over weight of ball goes under a clockwise torque. Okay, and then finally, we have this guy over here, which is of unknown size f. We're trying to find it, and he acts at 1 meter away from the pivot point. Okay, so I'm going to call this like F-app, this external applied force. Okay, so let's find out what all the torques are in terms of numbers. Okay, what's the torque due to this, wrong color. What is the torque due to this weight force of the stick? Now remember, torque is R times F, or F times R, however you want it. So R is the distance from the rotation point to where the weight force acts, which is at location 0.5 meters. So that's R, and all I have to do is multiply it by the weight force, which in this case is told to us to be 5.52 newtons. Okay? And I'm going to add on the other clockwise torque, which is from this hanging ball. Let's see. Its R is, it's told to us to be 0.683 away from the rotation point. So that's its R. Times the weight force, which is the mass of the ball, which is given to us right here, times, times 9.8. I'm going to leave it as little g because I'm going to go off the screen otherwise. Okay, and let's see, if we take out our calculator here and total up what this number actually is, 683 times 0.106 times g, we get that it equals 3.47. And again, this is a torque, so it's in newtons times meters. Okay, now what's the torque applied by this green force right here? Well, let's see. The distance, so its r, is going to be the distance from the x all the way out to where the force is pulling, so that's 1 meter, times the size of the force, which is this unknown variable f. Okay, perfect. We have 1 times f equals 3.47, so that just tells us instantly that f needs to be 3.47 newtons. Remember, because this is a meter, so when you divide both sides by meters, you get units of newtons, as you need to for a force. So this is the force that makes counterclockwise torques equal to clockwise torques. And as such, since we have picked just the right force that the counterclockwise rotations are balancing the clockwise rotations, the object sits perfectly still. Awesome. This is your first real torque problem, and this is actually not a very easy torque problem. There's a lot going on. So good job if you've managed to mostly follow along this example. And one more time, I just want to remind you that torque is a difficult subject, so as long as you have like a vague idea of what's going on, you're doing an excellent job, and as soon as you do a couple more examples, it'll really kick in and you'll get good at it. Okay, one point I want to make about this example is something that I didn't do. You might have wondered, well, this rod is, I'm going to do it in orange actually, this rod is being held up by like a tripod of some sort, so it's obviously getting pushed upwards by that rod there. Why didn't I consider that? Why didn't I put that into either a clockwise or counterclockwise torque? Okay, well, at first you realize it isn't really trying to make it rotate around that point at all. It looks like it's trying to make it rotate this way, but it's not making it rotate about this point. It's trying to make it spin otherwise. So you get confused if you do that. But the main point I want to make is, what is R for this force? Now remember, R is the distance from the X, so the rotation center, to the force. So the X is here, and the force is literally on top of it. So R is actually 0 for this force. Okay, there is 0 lever arm between the rotation center X and where the force is applied. Forces that are out here, they're far away from the X. They have a lever arm of 0.5, 0.6. But a force that's directly on top of the rotation center doesn't contribute to the torque. So therefore, it doesn't matter if I had included in here, the torque was 0 anyways. So I don't actually need to write that force in there. Excellent. Okay, now at this point we're going to start getting into a little bit more complicated examples. In practice, they're not going to get that much more difficult than this example. However, I want to give you, just like for forces, a sort of not foolproof process, but a reliable process that makes sure you can attack difficult problems without locking up. Because I had a lot of trouble getting stuck before I even drew a diagram on these problems. So I'm going to go through a systematic way that you can draw some, that you can attack torque problems by drawing clean diagrams and following a step-by-step process. Okay. Okay, and I'm actually going to do it off of that same example where we have a meter stick, a hanging mass, here's the center of the meter stick, and then there's some magical applied force being applied upwards. And we're gonna learn the process by following along and repeating what we did for that project. or for that problem. So step one is going to be to draw the free body diagram as usual. Now, fortunately, you won't have much to do with friction and annoying forces here, so you aren't going to care nearly as much about, or you won't have as much difficulty drawing the free body diagram. Okay, but you're going to want to pay attention to where forces act. And again, the difference is before, when we were doing free body diagrams, we didn't care. We just sort of put them all on the object. Here, you want to keep track of where the objects are pulling. So in this case, for my stick right here, I'm going to draw the forces on it. So I have some sort of normal force from the tripod, which again, later we'll find out isn't important, but for now, I'm going to draw it there. Okay. Let's see, I have the weight force, and again, the weight force needs to be drawn at the center of mass. Okay, so weight force is going to be here. I'm going to have, oops, my mass disappeared. I'm going to have this ball that's hanging around for no reason, its force, and then again I have this mysterious applied force. Maybe I'm holding up the meter stick. Okay, perfect. All right, step two, and this is a new step, it's not really difficult though, is you're going to draw an X, not the letter X, just a cross or something. You can use a star or whatever you want, and you're going to draw the X on the place where the object spins around. So, for example, this meter stick is like glued onto this tripod, but it's allowed to spin using this point as like a pivot. So in this case, we're instructed to draw the X right there, and maybe I'll draw it in green for ease of visual, although this diagram will quickly fill up with different colors. Okay, and this X is going to be really important because, remember, R, when you're computing torques, depends on the distance to the X. Okay, now there's a little caveat here, and it's that when an object is not rotating, so for example, the problem says all these forces add up so that the meter stick is perfectly still, find this force. When that's the case, when the object is not starting to spin, it turns out you can put the X anywhere. And you can actually use this to your advantage to make these problems really, really easy. And I'll show you how you can tactically decide where to put it. Okay. Now, this might not make any sense. It didn't to me. The reason you're allowed to put the X anywhere is this way, or is for this reason. We just did the problem with the X over on the left, but let's say I put the X here instead. If I computed the torques using this new X as the center, and I found that the counterclockwise torques were actually bigger than the clockwise torques, using this point as the center, the object would be starting to turn around this point, which it's not. The object is totally still. It's not spinning around any point. So that's just a vague derivate, or like a vague justification for it, but that is the true result. You're allowed to put the X anywhere unless the object is starting to spin about a certain point, and in that case your professor / the problem will tell you where the X needs to go. But you are allowed to put the X anywhere. And there's an art to this, because putting it in a smart place, and I'll define what smart is in a second, will make the problem easier. Often it'll turn it into a one-step problem, so it's really powerful. Okay, and a general rule of thumb, I'll write this in orange. Actually, I should probably be writing this in Galaxy Pen. We're going to have a really rainbow lesson. A general rule is you're going to put it on what I call annoying forces. So these are usually normal forces. And especially if you see a hinge in a problem. So for example, this tripod right here, that is a dead giveaway that you want to put it there. Okay. Now, if you get it wrong, that's okay. It doesn't mean you've done the problem wrong. You've just made the problem a little harder. You'll have to do extra steps. And I'll show you what happens if you get it wrong later. However, in general, you always want to do your best to pop the X when you have the freedom to on top of these annoying forces. So here, we're going to pop it on top of the Fn. And the reason is going to have to do with when we're writing out the torque due to Fn, its lever arm, so its distance to the X, will be 0. So it won't pop up in our equations. We won't need to know it, which is really, really helpful. Okay, step 3, we're going to break arrows that are diagonal. So break diagonal arrows into our standard left, right, up, down components. This is relatively rare. You won't need to do it too often, not nearly as much as you did for free body diagrams. But sometimes you'll still see diagonal things going on. Usually things will be given at nice right angles. Okay. Step 4. So if this were free body diagrams, we would be writing something like F equals MA, where F is all the rightwards arrows on your diagram minus all the leftwards arrows on your diagram. Now what we're going to do is this. We're going to write counterclockwise torques equals clockwise torques. Equivalently, some people like to do it counterclockwise torques minus clockwise torques, or some people do clockwise minus counterclockwise, but it all is the same equation at the end of the day, that the size of the counterclockwise torques should equal the size of the clockwise torques. And again, this is for the case where object is sitting still and it's not about to start turning. And again, these are called equilibrium problems, and they're by far the most common type. In the next video, which I may or may not put out, where we use moment of inertia to actually calculate how fast things start spinning, you'll need to do something specific, but we're not going to get into that. For now, you can do clockwise torques equal counterclockwise torques equal, and then all clockwise torques. Now, just like from F equals ma, this equation is really an instruction. Go look at your diagram. Oops, diagram. Which forces try to make it turn counterclockwise, and then again for clockwise. And the instruction says, don't write out those forces equal those other forces. Write out R times F for each of them, and then pop them into this equation. Right? So if we went back to our example, we didn't just say that weight stick plus weight meter stick equals this weight. No, instead we did torque due to the weight force, so we multiplied it by its R. Then we added on the torque due to the other extra ball's weight force, and then we set that equal to the torque due to the applied force, which coincidentally had an R of 1, so it looks like the force and the torque are the same thing. Okay, So just remember that you're not setting the forces equal to each other, you're setting R times the force added up equal to each other. Okay, perfect. So in our case, let's look at our diagram. Okay, again, we're able to ignore this force because it's located on top of the x, because we picked our x to be in a smart place. So we ignore this because it has r equals 0. Okay, what things are trying to make it turn counterclockwise? This guy, okay? His r was told to us in the problem to be the full 1 meter. So we have 1 meter times F applied equals, and that was all of our counterclockwise torques. Let's look at what forces try to make the stick turn clockwise. We have this force and this force, and the weight force was told to us to pull at 0.5 meters, and this one was told to us to pull at 0.683 meters. Okay, so let's write, again, we're not just doing weight force plus weight of ball force. We're doing torque due to weight force, so 0.5 times weight, plus torque due to this force, which is R times F. And again, the weight force was told to us to be, what, 5.02 newtons? 5.52. And again, we add on the torque due to the other guy, which is his distance to the x, times his weight, which is 0.106 kilograms times g. Perfect. Okay. Step 5, as usual, after we wrote out our Newton's laws, well, I guess sometimes you set things to 0 in Newton's laws. Here we've already set the angular acceleration equal to 0 because the object isn't turning. So we're going to skip that step, and we're going to go straight to count number of equations versus number of unknowns. By the way, if you guys haven't watched my past videos, know that I stress this an unfathomable amount because it's ridiculously useful, and it saves you a crap load of time. Okay, so in this case, we have one equation and one unknown variable, f app, so we are guaranteed to be able to find f app. Okay, now something I want to bring up is that step 6 normally would be just to solve, and I guess technically step 6 is solve the equation, or rarely two equations that you'll get, but you can't do torque along x and torque along y. It's all sort of in the xy plane. So I suppose really it's only ever one equation. What will sometimes happen is this step might fail. Okay? Sometimes there will be two unknowns and one equation. And if you've followed a lot of my other videos, you'll know that that is a sign that you're about to enter the hurt locker, because you're guaranteed mathematically to go in an infinite circle and be unable to find the answer. And the only way out ever is getting another equation. So the question is, when you run into this situation, and I'll show you how you can run into it without making any mistakes, what's your other equation? So I'll put this as step 7. And I call this step the emergency ripcord. Okay? You're going to write out F equals ma to get your second equation. Okay? What this will do is this will get you, usually the unknown force, as we'll see, will be the normal force. So this second equation will also contain that variable, So effectively, you'll go from one equation with two unknowns, which is bad, into two equations with two unknowns, which means you're guaranteed to finish the problem. So again, this is an emergency ripcord, and we're going to take a simplified look at how that might pop up in a problem. Okay, the example we're going to use is very similar to the one above, but I'm just going to remove some of the masses. Okay, all right. Let's say, and I'm going to title this example, when you need the ripcord. So you had one equation with two unknowns, and you think you were stuck. Okay. This is usually related to putting the x in, again, it's not the wrong spot, but it's in a disadvantageous spot. Or you're asked what is the normal force as part of your problem. Okay, so as an example, what if instead of putting the x here, we put the x in the middle on top of the weight force? What happens then? And let's say the question was find FAP and find FN. Okay? Well, we put the x in the middle, and we've already broken up anything diagonal, so it's time to write out our counterclockwise torques equals clockwise torques. Okay. With respect to this new center here, this is trying to make it turn counterclockwise, and its lever arm is now only 0.5 meters, right? Because the distance from the x to the force has changed. So we have 0.5 times FAP, and that is the only counterclockwise force acting. Okay, the weight force is now on top of the x, so its R is 0. So it doesn't have a torque, so we don't need it in this equation. And the only other force involved, by the way, I have deleted the extra hanging ball. I don't know if I said that at the beginning. I've deleted that to make the problem a little simpler. Only other force that's here is the normal force, and that's trying to make it turn clockwise. And again, its lever arm is distance to the center of the stick, where I've chosen to put the x for no reason. So it's 0.5 is its lever arm times the size of the force, which is Fn. So if you look at this, you say, crap, it's that dangerous situation. I have one equation, two unknowns. I don't know FAP and I don't know Fn. Yes, this equation tells me they're the same size, but I can't find either of them. So at this point, you look behind you, your parachute has failed, and you pull your emergency ripcord. So you're asked to write out Newton's second law, for all the forces involved, including this weight force. Okay? So remember, Newton's law is that all forces up, again, now we're not talking about torques, we're talking about just the force arrows. Forces up minus forces down equals m times the y acceleration of the object. And here, the y acceleration of the object is 0 because it's not starting to float upwards or downwards uniformly. Okay? If we look at our arrow, what arrows up do we have? We have FAP and Fn both pointing up. So they both come with plus signs because they're pointing up. And we have this weight arrow, 5.52, pointing downwards, and that all added up, according to this equation, should be 0. Aha, and now look. We have two equations and two unknowns, FAP and FN, as our two unknowns, so we are guaranteed to be able to find both F applied and Fn. Okay? And just another point, sometimes when your professor asks you what is Fn, it just turns out that it doesn't show up in this equation. That tells you that you should still pull the ripcord because it'll tell you what Fn is in terms of FAP that you just found from the other equation. Okay, perfect. Again, that's just an illustration of the general process applied to the example that we already did. As you can see, and sort of just like for forces, it's a long process to explain, but the actual steps are extremely short. And once you do maybe 2-3 problems, which we're about to do, it'll become more or less second nature for you. So let's get right into some extra examples. Oops. Okay, here we go. Okay, so I promised that torques are useful in like biomed and health sciences, and it turns out a very useful point is that your muscles and joints work just like extended sticks with pivot points and with forces applied. So a lot of the difficulty in these problems is translating it into a simple stick being pulled on by arrows, but once you do that, you'll see that it's just a typical force problem. So first task, I might even call this step 0, is reduce the problem to it's a stick nailed into a wall with some forces acting on it. And again, that's just to get all the complication of, you know, muscle here, joint here, where's what. This is just so it can be drawn really simply. So in this case, our diagram says we have a stick here. That's our arm bone. The elbow joint, where it's forced to rotate about, is right there. So I'm going to temporarily mark an X there because hinges tend to be where I want to put the X. Remember, they are the annoying force locations. Okay, I have some pull here. They call it M, but I don't like that. I'm going to call it F muscle. Okay, and I have this gauge pulling me to the right. So I'm yanking it to the left, but the cuff is pulling me back to the right with size 190 newtons. And the question is, what is F muscle? Okay. All right, step 1 has already really been completed. We drew a diagram. Step 2, we've already put the X in the smart place. I put it on the joint, which is, again, you can put the X anywhere and you'll be okay as long as you pull the emergency ripcord. But it's intelligent and it helps you solve the problem quicker if you put it on the hinge or the annoying forces otherwise. Again, that's almost always a hinge. Okay, so step 2 is already done. Let's see, what did I call step 3? Oh, breaking diagonal arrows up. Okay, all the arrows are already perfectly left or right, so I don't need to do that. You see how this process really becomes quite short when you don't have to write out the words. Okay, step 4, this is the actual meat of the problem. Counterclockwise torques equal clockwise torques. And remember, this says, hey dude, look at diagram. Do R times F for all clock or counterclockwise things. And set that equal to all the R times F added up for clockwise things. So let's see, what counterclockwise things do we have? We have this guy trying to make us turn counterclockwise. All right, what's the torque due to that muscle? Well, it's the distance between the X and where the force pull is, so it's just that, which is told to us to be 0.054. and you multiply that by the size of the force, which as of right now we don't know, but we're just going to leave it as a variable. Okay, and that's all the counterclockwise torques. This guy up here, by the way, which acts with a distance of 0.34 meters, all right, he's trying to make us turn clockwise. What's the torque using this as the center? What's the torque due to that force? Again, it's the distance between the x and where the force is applied, which is 0.34, times the size of the force, which is 190. Okay. Step 5 is going to be count equations versus unknowns. One equation, one unknown, so we're set. And again, step 6 or 7, depending on if you count the ripcord as a step that you do every time, is to solve. Right? You've passed the check that you've done all the physics required. It's just going to be algebra 1 / maybe a system of equations. So in this case, I just divide both sides by 0.054. Let's see. We have 0.34 times 190 divided by 0.054. And this gives us F muscle equals 1302 newtons. Great. See how little work that problem was once we actually boiled down the steps to what you do in practice? Awesome. Okay, let's do one more example, and then depending on how I'm feeling, we may or may not do a challenge example. Okay, this one is going to be back to the meter stick with masses hanging from it, which turns out to be what is most common. Okay, so step 0, again, if you want, you boil this down to a stick, but really that's already kind of a stick. So we're going to go straight to step 1, which is draw the free body diagram. So let's see. We have this long stick. Let's see. We have a 25-gram mass hanging there. And I'm just going to go right ahead and instantly convert masses to weights, which I don't always do, but I'm going to here. So I have 25 grams. Oops. 25 grams is 0.025 kilograms. I'm going to multiply that by 9.8 to get the associated weight force. So this force right here on your calculator will spit out 0.245 newtons. Okay, we have this 75-gram mass. And if you plug that into your calculator, that mass in kilograms times g, you'll get 1.715 newtons. Oops, wait. Sorry, I typed it in wrong. 0.735. Okay, there is some sort of normal force because the meter stick is being held up by this hinge. However, we're going to put our x there, so in practice we won't really care about the size of that normal force, but I'll draw it in there even though it won't enter into the torque equation. Okay, and finally over here I have this mystery mass m2 and the associated force m2 times g, and that force is acting out at, well, it's at 85 centimeters on the meter stick, but remember, it's distance to the x that we care about. Okay, perfect. So we've done step 1. We've already put the x in a smart spot on top of the hinge. So step 2 is done too. No forces are at anything other than right angles, so we don't need to include any sine thetas or do any decompositions. So we're already straight on to writing out step 4, which is counterclockwise torques equals clockwise torques. Okay, what forces try to make this turn clockwise? Well, we've got this guy and this guy. They both try to make it turn like that. Okay, torque due to each of them, remember, it's the distance from the x to where they act. So for the 25 grams force, that's 1/2 of a meter times the size of its force, which is 0.245. And I add on now the same thing for this force. How far is it from the x? Again, it's located at 20 meters from this side, but we don't care about that. We care about distance from the x, which is going to be from 20 or from 50 to 20, which is 30 centimeters, or 0.3 meters, times its force. Okay? Those are all the clockwise torques. Put a fat equal sign in the middle. And this force is our only clockwise guy. Okay, what's his distance from the x? Let's see. He's located at 85, and the x is over here at 50. So this is 35 centimeters, or 0.35 meters. Maybe I should do this in blue because I've been doing all the distances in blue. And I multiply that by the size of his force, which is m2 times g, and remember g is just shorthand for 9.8. Okay, perfect. Now I check, do I have the same number of equations and unknowns? I don't know m2, that's what the question is. And I have one equation, so I'm all good. One equation, one unknown. So the last step will be to just solve for m2 algebraically. So I'm going to total up everything I see on this side. 0.5 times 0.245 plus 0.3 times 0.735. I get 0.343. And if I combine the 9.8 and 0.35, I get that. Divide both sides by 3.43. And I get m2 equals 0.1 kilograms. Awesome. This is a classic problem that professors love to pop on tests. So if you more or less followed along, again, it comes with practice. If you haven't done it yourself yet, don't worry, it'll come sooner rather than later. Excellent job if you more or less followed along with this. You've come really far in this lesson because torque is a difficult concept. Okay, here is the challenge example of this video. It's a challenge example because there's a non-right angle involved. So if you're feeling a little bit out of energy, if it was a tough subject to learn, feel free to either take a break and come back to this or not look at this at all. It is a relatively challenging problem, but we are going to be able to tackle it without too much difficulty. Okay, so challenge example. Okay. Step 0 is sort of going to be to translate this into a nice looking system that is sort of the same step as step 1, which is drawing the free body diagram. So let's see. We have a gate here. The center of mass of the gate is right here. It's being pulled on by this rope. Let's see. We don't know the tension of the wire, but we know that this angle is 45 degrees. Okay, obviously the weight force, or not obviously, I told you towards the beginning of the video, the weight force pulls at the center of mass, and it tells us the weight is this variable w, so we're just going to leave it as a variable for now. We're going to end up finding like t equals 2 times weight, or t equals 3 times weight, and that'll be our answer. The way this problem is phrased, you assume w has been given to you, and you are expected to phrase your answer as t equals half of w, or t equals 2 times w, something like that. Okay, let's see. We have 2 hinges here. That's another difficulty here. However, it says the tension in the wire has been cranked up just enough that the horizontal part of the force between the bottom hinge and the gate is 0. So in general, you could have a force of the hinge pulling up and to the side, but in this case we've tuned T so that this left-right arrow is not there. Okay, and then we have this upper hinge as well. Maybe I'll draw it like this. Okay, I'm going to call this hinge 1. I'm going to call this lower 1 hinge 2. Okay, so we've drawn our free body diagram, and now it's our task to draw the X at a smart place. Oh, by the way, I should have mentioned this hinge actually is up at the top corner. Okay, so we want to put our X at a smart place, and there's 2 hinges, so I'm going to pick the hinge that's more annoying, which is this one, because it hasn't been carefully designed so that its horizontal force is 0. This hinge is annoying. I'm going to put the X there, so that sucker won't affect us at all. And also, sorry, I'm now noticing I should have drawn this dot all the way at the bottom here for the bottom hinge. Okay, so I've put the X down. Now, I have a diagonal force. If we want, we can break this up, but really, you don't need to decompose it yet, unless you're using Newton's laws. Ooh, sorry, not unknown. Unless you're pulling the ripcord. Unless it turns out that you need the ripcord. So we're actually not going to decompose t yet, and if we need Newton's laws, we'll go back and do it so we can get the y arrow. Okay, step 4 is going to be to do counterclockwise torques minus clockwise torque, or equals clockwise torques. Okay, let's see. Again, we're fortunately able to ignore these suckers because they're on the X. So the only forces we have to worry about are this guy, and he makes it counterclockwise. This weight, or this hinge force, which actually doesn't really try and make it rotate in any direction. The reason being, here's R, and here's the force. Okay? The question is, does this force cause any rotation at all? The answer is no. And the question might be, then what's his torque? What are we doing with it? Are we putting his torque in the equation anywhere? And the answers are related. It's that this torque will actually be 0. And again, the reason is that this arrow, so R for this guy, again, R is the arrow from the X to where the force is pushing. Normally, you need a force arrow to be perpendicular to that to have torque. If the arrow is in the same direction or opposite direction as R, you have sine of theta is sine of 180, which is 0. So the torque equation automatically encodes this fact that these arrows, since they're not perpendicular, we need to use times sine theta, and it turns out the torque due to that force is 0. So we actually don't even need to consider this guy for our torque equation. So we only have this force going counterclockwise and this weight force going clockwise. Oh, and by the way, I'm now realizing that we should probably call this length L. Okay, let's compute the torque due to this guy. Okay. Now, as usual, it's distance from the X to where the force is applied, which in this case is L, some unknown variable, times the size of the force, which is that unknown variable t. But remember, the arrow and the force are not at right angles, so now we also need to multiply by sine of some angle. Now, you might jump to the conclusion instantly that it's 45, but if you draw out the arrows, so here's R, and the T arrow goes this way, and this is 45, so technically the angle you need is 135, right? 180 minus 45. However, luckily, sine of 45 and sine of 135 are the same thing, so you get away with it if you accidentally did sine of 45. But I'm going to be really correct here and do sine of 135. Okay, perfect. That's it for that force. How about this force right here? We're going to do the torque due to it, so we do the distance between the x and it, right? This is r. Right, what is this distance? Let's see, we're going to need to do a little bit of trigonometry on this. So if this whole side length up here is L, that means this is L over 2, and the weight is acting in the center, so you can sort of see that this must be a 45-degree triangle. And the rule for 45, 45, 90 triangles, you can also do this with trig, by the way. You can do L over 2, or cosine of 45 equals L over 2 divided by hypotenuse, and you'll come to the same conclusion. But it turns out that the result is that the length of that diagonal right there is L over 2 times the square root of 2, also known as L divided by square root of 2, if you choose to cancel numbers. Okay, perfect. So that's the distance from the x to where the force is applied. Now we multiply by the size of the force, which is just W. But hold on, the R arrow here and the weight arrow are not pointing in the same direction or perpendicular, so we need to use the sine of theta additionally. So what is the angle between these two arrows? Let's see. Again, it's tempting to just jump to 45, but you want to double check it before you do anything. Okay, so coincidentally, since 45 is half of 90, this angle right here is also 45 in between the two arrows. So you, once again, even if you blindly did 45, you would get away with it, but you got really lucky, because if this angle were 30, this angle would be 60, and you get a different answer. But again, the proper one to use is this one, the angle in between the two arrows. Okay, perfect. Now all we need to do is look at both sides, because we have our finished equations, and we count how many unknowns and how many equations do we have. Well, we have one equation. Let's see, we don't know L, however, it cancels from both sides of the equation. We don't know T, so that's one unknown. And it sort of feels like we don't know W, but remember, the problem is it's assuming that it tells us the weight, and it expects our answer to be T equals 2 times weight, or whatever. So we basically pretend that W is a variable that we know for the purposes of counting equations. So we do know W, so it's not an unknown. And we have one equation, one unknown, so we're guaranteed to be able to finish this. Okay. So all it is going to be cleaning up our equation. Okay, if you punch sine of 135 and sine 45 into your calculator, it turns out they're the same number, so they go away. And you're left with this wonderful result. T is root 2 over 2, also known as 1 over the square root of 2, times W. And just as a recap, by putting the x in a smart place, we instantly eliminated all these annoying hinge forces that we didn't know from the equation. And coincidentally, since this hinge only had an upwards force, but its R was in the same parallel direction, the fact that you have to multiply by sine of theta when they aren't at right angles meant that the torque due to that force was 0. So that annoying force also was out of our equation. And we were left with this dramatically simplified torque equation that only had 2 things in it. It's like a free body diagram problem. If you only had 2 forces, it would be really easy. So again, this just really shows you the utility of picking your x and putting it in a really smart place. All right, guys. Like I said, that was a challenge example. That's a really challenging problem. In class when we did it, students took probably 30 to 40 minutes on it, so don't feel too flustered by it. It's very difficult. However, if you go back and approach other problems now, you'll probably feel a lot more confident in being able to approach them, seeing how putting the X in one spot can really make your life a lot easier. But with that, guys, I want to congratulate you on finishing up torque. This is really the last truly hard thing to learn in Physics 1. And unfortunately, it comes towards the beginning/middle of the semester rather than the end. So do pat yourselves on the back. There's a lot of cool, interesting stuff ahead. If you haven't done conservation of energy yet, that's a great topic, a lot easier, a lot more useful in my opinion. And then you'll often get into some interesting topics like waves and pressure of gases. So with that in mind, pat yourselves on the back, and I'll see you in the next video. Remember, feel free to like the video, subscribe, and share it with classmates if you find it helpful. Till next time, guys, see you then.